Hello everyone, welcome to my video about an assignment in Embedded System Programming course at ASU. Its title is Accelerometer and Gyroscope Sensing and Filter. The problem statement of this assignment is to develop an application program that measures the orientation of the object in 3D space. So an accelerometer and gyroscope sensor is attached on the body. Sensor data is collected and processed by a signal processing module filter. And this processed output is sent to a display program to illustrate the movement. Given that the display program is an executable built with Unity and is running in the host, and packet should be sent via stream socket to specified port at the host. We are using Intel Galileo board in this assignment, which is having 32-bit processor running at 400 MHz, having 512 KB static RAM built in. The motion sensor we are using is MPU-6050, which is the world's first and only 6-axis motion tracking device designed for the low power, low cost and high performance requirements of smartphones, tablets and wearable sensors. This sensor's gyroscope full range is user programmable from plus and minus 250 to plus and minus 2000 degrees per second. It's user programmable through its dedicated I2C sensor bus. The full scale range that we are using in this assignment is plus and minus 1000 degrees per second. The Unity program consists of an aircraft in 3D space. These aircrafts rotate according to the given data, which is received from the application through TCP/IP socket. For better understanding of the Unity, let's have a short demo. So this is the Unity program consisting of aircraft in 3D space. We are giving 127.0.0.1 as our host address, as it is local address for demo purpose. And other three options are reset position, stop, restart. On clicking restart, the program starts to accept TCP/IP packets. So let's have a look at an application written in Java. So a socket is being created to this address at 9999 port, and outstream is also being created. At first we are waiting for 2 seconds so that we can highlight the Unity program. The next we are giving the values, positions and as well as angular velocities. Angular velocity we are giving as pi radians for only in x axis only, so that to understand the Unity program, and we are sending the data and again we are sleeping for 2 seconds. Next we are rotating the object in only y axis. For that we should negate the previous x axis value and give the y axis angular velocity value, and again send the values and sleep for 2 seconds. Similarly for z axis, and finally to stop it we are giving no rotation. So let's restart the program and compile the application. Yes, it's compiled, and let's run the program. So this is how the Unity program executes. Now let's look at the hardware setup. The application or filter is running in Galileo board, which takes the sensor data through I2C bus, and the process data is sent to the Unity program through TCP/IP socket connected through the Ethernet port. Let's have code explanation now. So this is the program written in C that runs on Intel Galileo board on compiling. So we are using first main underscore 4.c. So all these are the header files. The Carmel filter and MPU-6050 defines are exclusive header files that I will be explaining soon. And these are all the defines that I am going to use in this program. I am going to keep interrupt timeout to be 3 seconds and sampling time 4 milliseconds, and these are the GPOs that I am programming for interrupt, and these are the global variables that I am going to use in the program. The first function is export GPIO. So exports the GPIO and sets the direction. So in the buffer we get the value and we export it according to the given direction. So that file handle is open and written according to out or in according to the given GPIO direction, and file handle is closed. And next is open GPIO function. This just opens the given GPIO value and returns the file handle. So this is the GPIO file we are using, and return the file handle. Next write GPIO function. This opens the GPIO value file and writes the given value and closes the file handle. So that value is going to be present on the GPIO. So next unexport GPIO, it just unexports the respective given GPIO, and this is initialize GPIOs. In this initialize GPIOs function, we initialize the required GPUs and set their direction. So if it is error, it will be written -1. And this is deinitialize GPUs function. It simply calls the unexport GPU function of all the initialized GPUs. Now this is the main function, send to socket function. So here the x, y, z, xr, yr, zr values are taken into buffer and sent to the Unity program through TCP socket programming. So the format is clearly mentioned in this. So if that write is passed, it will just return 0, otherwise it will be printed error. And next, initialize socket function. So it creates the socket with TCP IP properties, and the port number we are including is 9999. That is what it accepts the Unity program. And next, the IP we are giving from arguments. So and finally it's connected, and connection successfully be displayed if it is successful, otherwise failed. Next, MPU write function. Here the data is written to the offset through I2C port, and this is MPU read. In the MPU read, the offset is at the given offset, the first the offset is written and the data is read from the read function, and this is get motion rates. So this is the main very important function to get the sensor values. So we are giving the offset value of RA axle X out H. From there all the 14 registers we are going to get the values. So we read all the 14 bytes of values consecutively and are stored into a variable and processed accordingly to get the acceleration out and gyroscope out in respective axes. So and next, the initialize motion sensor function. In this function we are initializing the motion sensor MPU-6050 through I2C bus. So first we write the device address. The device address is given in the header file. So here in the header file it's given, it's 0x68, as we are connecting the AD0 to ground. So the rest are the register addresses taken from the register manual. So if you come down, you have here accelerate out. So this is the continuous 14 bytes of sensor data. So first we are reading who am I register, we need to get 0x68, otherwise it's not working. So later on we are setting the sampling rate divider value to 31 for 4 millisecond sampling time, and we are enabling the interrupts so that based on the interrupt only we will be reading the sensor values. So later on, Kalman filtering function. This is the main function where the filtering is done using Kalman filter. So these are all the structure variables for Kalman. So for the first time we are keeping the values, we are storing the gyro sensor values and setting up all the positions. So the x-axis and y-axis Kalman angles are resetted. So roll and pitch is calculated according to the given function, and it's the stored in x angle and y angle. Z is calculated through regular integration, and in the next coming times the roll and pitch will be calculated according to this function, statement equation, and based upon these conditions the Kalman x angle and Kalman y angle will be computed. So this is where the Kalman estimate angle is being called, which is present in Kalman.h file that I will be showing you soon. And that Kalman x angle and y angle are subtracted from the previous angles that has to be sent to the Unity program, and they are converted into degrees to radians and they are stored, and the z axis normal integration is being computed here. And this is normal filtering function. Here no filtering, we are not doing any filtering, we are just getting the values and just removing from the old values and sending the changed value by converting it into degrees to radians and sending it to the unity. So finally, mainly the gyro x out unity, the underscore unity values are being sent to the unity program. So this is reset unity function that mainly we are not using. This is the mouse thread function. So initially we have some implementation. So to switch from normal filter to Kalman filter or Kalman filter to normal filter by enabling this value, though right now we are not using in this program, but this is an enhancement. So this is the main sense thread. Here we are using pole FD. Based upon the rising edge, we are sampling the sensor values. So we are keeping open the GPIO pin value file device. So upon stop only we will be stopping this while loop, continuous loop. So once we get the interrupt value, interrupt from the sensor, we will be going to read the sensor values through get motion rates function, calling get motion rates function value. So since basically it's by default enable Kalman filter is 1, Kalman filtering will be done and the computed values will be sent to the socket, and this is done continuously. So and finally when the stop is observed, will come out by resetting the unity figure. So this is the main function where all the threads are being called and all the initializations and deinitializations are done. So we need to pass the arguments as this. We have to give the IP of the unity program, and next after getting it we will be initializing the GPIOs as stated above. So you need to give the IP address, please remember it, and we will be initializing the socket and motion sensor, and we'll start sensing the call the thread. The mouse thread is right now uncommented, so the thread will be stopped only when we encounter E value. So once it will join and close all the connections. Now let's look at the Kalman.h file. So this is taken from the internet from 3JK Electronics. So credits are given to them. So what we are creating a structure of having different values like Q angle, Q bias. Those are process noise covariance matrices and measurement noise variance. And this is angle calculated by the Kalman filter, and bias, gyro bias, and the rate, unbiased rate calculated from the rate and calculate bias. So PK or error covariance matrix and Kalman gains. So Kalman estimate angle is the main function that we are going to call. So we are giving the new angle rate, and sampling time, and the Kalman filter structure. So the rate is updated here and angle is updated here according to the given equations. The process covariance matrices are updated according to the given equations, and we will be soon calculating the Kalman gain according to the given equations, and the new angle is computed from the new angle minus Kalman angle. We are calling the same function for x and y angles by giving the structure, so the respective structure will be processed. Now let's have a demo. This is a sensor that I have mentioned you in the presentation. It's connected through I2C bus interface to the Intel Galileo board, on which the application program is running, which is written in C. Now I will make the application, compile the application and send it to the Intel Galileo board to run it. So it send it. Now we will be ready to execute the motion sensing application, giving the host address. So in the Unity program we have given the host address, and we restart the Unity program to start accepting the packets. So we will be holding the sensor, and I started executing the program. So this is how it rotates. So the object rotates according to the sensor, so in both the x, y, z axis directions. So this is z axis and this is x axis. So because even though with using Kalman filter some noises are coming, so because of that it's not being completely accurate. So the way we tilt the sensor, it's reflecting on the image. But even though with those so many noises, the image is rotating according to the sensor. So this is the demonstration of my program. Thank you for watching. If you have liked the video, please click the like button below. Thank you.